Today we're going to be talking about retrofitting grid-tied systems with battery backup. This is Mark McHenry, and I'm here with Doug Grubbs, Morningstar Applications Engineer. As we conduct this webinar, please text any questions that you might have in the chat box at the bottom of the GoToWebinar pane, and we'll address these questions at the end of the presentation as time permits. We're also going to be making a recording of a version of this webinar available on our website. So make sure you bookmark morningstarcorp.com and go to the resources and recorded webinars tabs to access the recording so you can share it with others. So let's get started. First, I'd just like to pose a question: why is it so important to retrofit grid-tied systems with battery backup power, or with backup power, I should say? So let's take a look at some wire diagrams, and this will help give us the answer. So what you're seeing here is a diagram of a simple, efficient grid-tied PV system for a residence or light commercial establishment. And on this diagram, DC power is provided from the PV array to a string inverter, and that DC power is converted to AC power, and that's sent to your main service panel to run your loads. And any excess power that doesn't have to be used will be sent back to the utility for a credit to reduce your bill. Sometimes people call this running the meter backwards or net metering. So this is a very simple, efficient, and very effective installation. But if you're a PV installer, after someone purchases a grid-tied PV system from you, you probably encounter the question, what happens when the grid goes down? And if you didn't get asked that question, you should make people aware of the answer anyway so they won't feel misinformed and disappointed later. So let's take a look at what happens when the grid goes down. And as you can see on this slide, when the grid goes down, the string inverter, whose operation is dependent on the grid, gets disconnected and doesn't deliver power to the main service panel, nor to the utility. And this is by design and by code, since if the connection is maintained, you'd create an electrical hazard to workers who are trying to put the utility power back online. And therefore, during a grid outage, even if you have a solar array, you have no power. And almost all of the residential and light commercial grid-tie solar systems that have been installed throughout the world over the past 2 decades rely upon utility power to operate. And recently, storms and infrastructure events have caused a growing number of consumers to experience the fact that their grid-tied solar system is useless during a power failure when the grid is left stranded. So that's the reason that we have to retrofit existing grid-tied systems with backup power. And we're going to take a look at some of the ways we can enable backup power when the string inverter is disconnected from the utility and your main service panel. But before we do that, I just want to launch a quick poll to ask you, the audience, what you think is the biggest obstacle that's preventing the installation of backup power. So let me just launch this poll, and you should be seeing it now. And if you'd be kind enough to just reply. And I see we have several folks are replying now, so that's good. Is it A, is there nothing really preventing you? Perhaps you're already doing a lot of installs, or if you're a residential customer, you've already installed backup. B, is there no demand for it? C, is it too complicated? D, is it too unreliable? Or E, does it cost too much? It looks like we got about half the votes in, a little bit more, but we're going to just run this a little bit further. And just for about another 15-20 seconds, I just want to remind everyone, if you just joined us, we are going to be making a recording of this webinar, and we also invite you to text any questions that you might have in the chat box at the bottom of your GoToWebinar pane, and then at the end, Doug and I will address those questions as time permits. So great job, folks. Looks like we're right up, getting close to about 75%. So I'm going to close the poll now, and we're going to show the responses. Close that, and we'll share it. And as you can see, what we're looking at is 21% said there's really no obstacles. And then we have 61% said that it costs too much. We have a number, about 18% said that it's too complicated. So I guess this doesn't surprise us too much that the majority of people said that it costs too much. So hopefully we're going to help out with some solutions that we share here during this webinar. So let me close out that poll. Let me progress forward here. And we're going to talk about backup options, and I'm going to hand off to Doug, and if you can take us to this slide, please.
Thanks, Mark. As you know, before working with Morningstar, I was designing grid-tied PV systems in South Jersey. The integrators, 3 out of 4 of them that I worked with, never offered solar PV battery backup solutions. And even when the customers asked about it, our salesman recommended generators over PV backup and would explain that battery banks cost too much and traditional AC coupling is going to hurt the efficiency for payback. So that was prior to an early snowstorm in 2011 and Hurricane Sandy in 2012, kind of 2 years in a row being hit hard on the East Coast, which caused major utility outages in the region. And so some solar PV integrators started offering AC coupled solutions for retrofitting existing PV systems for battery backup, but many still found that to be too complicated and problematic or too expensive since it was not scalable. What we need are more cost-effective solutions for battery backup with grid-tied solar PV systems. Our new direct DC transfer charging solution can provide such a solution by itself or combined with these other solutions. So, looking at generators, generators can require maintenance, and unfortunately, a lot of people do recommend generators, and some installers actually install generators also, but they requires periodic maintenance many times, depending on the type of generator you have. It can be a problem getting fuel for it. It's noisy. It can be some of them are more reliable than others. There's CO2 emissions, and one of the things is that you have a PV system that sits idle during a utility outage, which customers are kind of like, wow, that's too bad. I got all this power sitting there and I can't use it at all. So hence many people go with our existing PV systems. So existing solutions include, the next slide, the traditional DC coupling solution, which has been around for well over 10 years, probably since the beginning of grid-tied systems, because originally all systems were battery-based inverter charger systems. So it was just a matter of making an off-grid system, which is basically a controller, a battery bank, an inverter charger, and then just taking the output and feeding the grid and critical load subpanel. So one of the problems with this is that the grid selling is not efficient as with the string inverter. And also, if you're retrofitting a system, it's hard to just replace your string inverter. You're basically throwing away a perfectly good inverter and opting for this inverter charger system. And another problem is that the controller sizing it's not scalable, meaning that you wouldn't want to use an oversized PV array, which would limit your power to the grid. You want to use maximum power. So these are two things we'll be talking about a little bit more, but basically it can be pretty good for a new system, but you'll take a hit on the grid selling, which has always been a concern. And going on to AC coupling here. So this has become more popular recently. I don't know how long it's been going on. I guess there's been some grid island systems for many years, and the problem here is that it does work pretty well, but the most string inverters cannot reduce power. The inverter charger sizing has to be made so it can handle the full power from the string inverter, and that means that when the string inverter comes on, when your batteries have to go into charging, the string inverter might throw out max power for that string inverter at that moment, and then you could just like slam that back to your inverter charger and even damage it, or it won't work basically and shut off. So it can protect itself maybe, but it could also damage it. So the battery has to be sized for the max charging current also. So you have to size your inverter charger. You can't scale it down at all, and so it makes it for very expensive options. If your string inverter's a little bit larger, over 4 or 5 kilowatts, you're not going to be able to do it with the little 4 kilowatt backup inverter charger. You're going to have to size it at least as big as the string inverter, and a little bit bigger actually, so you're sure it's going to be able to handle that full power. And so the battery also, in order to be used, you can't just throw in as much current as you want to a battery. There is a limit, and so if you want a smaller system, the battery sizing has to be sized to handle the full current from the charging sources. And then on-off switching is another problem, because the batteries don't really ever get fully charged. It's like having a UPS and a solar battery bank in parallel. So basically, when you get to about 80% state of charge, if you're familiar with battery charging, it should go into absorption, the third stage or the second or third stage of charging, and it doesn't because it can only do bulk charging, or that's all on, full power, or off. So on-off switching will shut it down, the inverter, when you're about 80% or 80 to 90% state of charging, and never get to full battery bank. So part of that battery bank goes unused. And then you can, and we're not talking about every type of string inverter. Some string inverters can operate at reduced power levels that will taper down the power as required for the battery bank. And also, if you want to add more complication, you can add diversion charging control. Many people have used our TriStar controller, which can be used in diversion charging mode with these systems. So this means you end up with oversized systems often, much more than the customer may need. And then AC coupling also is not always supported by some string inverter manufacturers. They will not, if they find out you've put in an AC coupled system with their inverter, they may not recognize the warranty in some situations. Inverter charger shutdown, that means that in low voltage disconnect at night, which is somewhat common with these off-grid systems with a small battery bank, can happen that the inverter charger shuts down and would require a manual restart in order to continue, or some kind of automatic restart system that not all inverter chargers for these systems have. So there's got to be some kind of relays or something to make it turn on just in case it goes into LVD. Because once the inverter charger's off, there's no charging. And this will also result in you're limited to using it with smaller string inverters in order to get a moderately moderate pricing for these kind of systems. So anything over 4 kilowatts, you may need to really upscale that inverter charger. You may need to use inverter chargers in parallel. You know, once you get above 10 kilowatts, you're almost like AC coupling becomes almost, unless you exchange string inverters with smaller inverters, you're really running into trouble with sizing. And so our direct DC transfer switch will take care of a lot of these issues, both with DC coupling and with AC coupling. This is a DC coupling solution, but it's an AC inverter charger solution also. So you're a grid-tied inverter solution plus DC coupling, direct DC charging also in the same system. So some people have considered this as a real game changer. You can use your existing PV array. You don't have to redesign it. You can find a simple way to integrate it into any PV system just about, and it is scalable, so you can offer some lower cost options which will be easier to sell to customers. And so looking at this concept, we've had this drawing out for a couple years now when we introduced the 600 volt, and this is one of the applications that we've been looking for. And basically, this is a diagram of basically what we have with the DC transfer switch. This shows the DC transfer switch in front of the of our equipment and the grid-tied inverter. So this is actually what we have. We put the DC transfer switch inside our box, inside our DB box. So it's all in there, but this is actually what the circuit will look like if you were to redraw it like this with the DC transfer switch. So as you can see, it feeds the grid for high efficiency here, and it's you get high 4-stage charging, very efficient. It's a cost-effective design because it uses your existing PV array. It supports more inverter charger and battery choices, and you get it's a better alternative than AC coupling, and it's not problematic and gives you more flexibility and better charging efficiency. So going on to the next slide. So how do we get to an effective low-cost entry point? So in order to lower the cost, as I said, when we used to explain it to customers, the batteries are the cost you're trying to avoid. So there's also the problem with existing DC coupled systems that you can't really use the existing array or subarray unless you use a 600 volt inverter controller, which you can do with our system as well. Our TriStar MPPT 600 volt can. You just swap out a string and do DC coupling, but you lose the high efficiency for the string inverter. And it also, you cannot oversize the array and take advantage of what we're going to go over next, is that in order to get to smaller battery banks, you want to do it without creating a smaller PV array. So you can make a smaller PV array and do DC coupling, or make a smaller PV array and do AC coupling, but you don't get full charging on half your system goes to waste, or whatever's not connected to your direct DC coupled or AC coupled system. You just can't use it because you're maxing it out. So you can reduce the maximum charging current using the same size PV array. This reduces you to a max charging current on sunny days when you really don't need that energy. The battery's going to be full. And then with a smaller battery bank, you also get the full power on the cloudy days and when there's little sunlight. So you get the critical charging power, but you don't get the excessive full sun charging, so you can scale it down. So this also fully charges the battery. That's an important effective in terms of effectiveness. If you don't fully charge your battery, you're really kind of wasting buying a battery bank that you can't really use part of it. There's the suitability of your inverter charger. You may have to oversize with an AC coupled system. You may have to go to a larger inverter charger than you would want. I mean, if you had the choice of, if a 4 kilowatt inverter was able to feed all your loads, why would you go to an 8 kilowatt inverter or something bigger than you really need? And then also it gives you the opportunity to look at a single phase, non-split phase inverter chargers as a solution also. So you can use, not that you're limited to single phase inverter charger, but that is an option now that is not an option with AC coupling. So in order to realize lower cost options, you may have to talk to the customer about conserving energy and how much power they really need versus what they want. And you know, when you have one solution that costs you know, quite a bit, that's going to be hard to sell. But if you can say, well, you can scale down a little bit, look at just running, how many loads do you want to go with, and see if you can find an option that's something that's more realistic. People always have to look at energy conservation with standalone or battery backup solutions. So we're talking about limiting your energy consumption during the outage, and these are several ways you can do that. Higher efficient AC loads, replacing light bulbs, replacing refrigerators, washers, that kind of thing. Fewer AC loads, just have fewer circuits possibly, or limited number of loads running, and turning off loads at night, for example. Ways of reducing power during the time that you have outages and can make your batteries go a lot further. I mean, these would be recommendations for anybody having battery backup, really. And then, but you can also look at what is really critical and what you'd like versus what you would want in all your best case scenario. So we're also looking at flexible load usages, maybe not running your vacuum cleaner or something if it's a rainy day or something. So wait till your batteries are fully charged before you start running certain loads. And then also considering the possibility of generator charger for battery backup to charge the batteries if the batteries get low. So this really, the first they cut generator run times to AV, and then you can really cut this down to possibly not even needing it during the outage, but it's there because you want to size your battery smaller and not have to go for several days of autonomy during a long outage. So our direct DC transfer charging is actually less complicated. It seems like more components. It is more components, but when you have to oversize your AC power and then adding more charging, this is one place where it really gets simple, because if you want to add AC charging to an AC coupled system, you have to add additional AC coupling, and that AC power is already a lot of power, and it's more than you may need. So to expand it and then not even be able to reduce the power charging limit, that's really going to give you a lot of complications in that system. If you've ever done any parallel systems and adding additional AC coupling, and then three-phase especially, could be really complicated. So what we have is less complicated. You're not even worried about what kind of inverter you have. Basically, you would size it with a maximum ISC of 24 amps. That's for the 30 amp switch. So there's an NEC limit on the current. And then a maximum VOC, typically around 570 or less. You can go above that, up to 600 without damage to the controller, but you may find that in the winter it may shut off due to high voltage if it's above 570 in the morning in the coldest conditions. So that's something you want to look at our online string calculator to determine if your sizing for the TriStar MPPT 600 volt controller. The pre-wired transfer switch with the MPPT controller with the ground fault protection device is really nice because it's basically about as simple as connecting a disconnect switch in a system. In that the AC side is just between the inverter and the array or subarray. You just have a switch there. Basically, you have an input from the PV array, an output to the grid-tied inverter, and then you just need to connect the battery cable to the battery or to a terminal or to a battery bus bar, which is mostly included in most inverter charger kits. And so getting onto the inverter chargers, there's lots of inverter chargers to choose from. You're not trying to consider, well, what size inverter charger do I need for this inverter? You're trying to think of what size inverter charger do I need for my loads, and what size inverter charger can I put on this battery? So you want to match the battery voltage and get the grid-connected BOS kit. Some of these come pre-wired, so all this stuff should be rather straightforward and basic as far as anybody that's done an inverter charger system. Should be very familiar with all this. And then with our controllers, there's plug-and-play options. So there's presets, factory presets for certain types of batteries. You may not even have to go to a screen to have to program it. You can just set it up for 48 volts and set it for sealed batteries or the setting that's needed for the batteries, and just let it rip. We also do not require any type of diversion charging control and all that design hassle with that. It will continue to charge at the batteries with 4-stage charging without having to do that. It continues charging with inverter, even if the inverter charger shuts down due to low voltage disconnect. So you don't need to add any switches for that. And then we get very high efficiency, and for the battery charging performance is where you really want to go with DC coupling. Because you do get high efficiency, you do get full state of charge. The factory presets you have factory presets, or you can make custom programmable settings to tweak them if you want, or to use any type of battery, such as lithium or other types of batteries. We also, last thing I want to mention is that it is clean. It will not create more pollution, and it will use your existing PV array, and it's low noise.
Okay, well, thanks a lot, Doug. I guess this is where I kick in again. So we're going to talk about the components of a direct charging solution with DC transfer switch backup solution. So you can see here, this is the equipment that needs to be added to the existing grid-tied system. We're going to be adding our 600-volt controller, the Morningstar ground fault protection device, batteries, and we're going to also add an inverter charger, a BOS for battery backup, and a critical load subpanel. There may be some other components that, depending on your local regulations, you might have to add some other components as well. So let's go ahead and take a look at the first component we're going to be adding here, and that's our 600-volt solar charge controller. Again, this is a very high voltage controller that accommodates grid-tied systems. Oftentimes in grid-tie, you're running string inverters at 200 or 300 volts or more. This controller allows for incremental module additions without string sizing issues. Peak efficiency is close to 98%. It's preset for 48-volt battery systems, but you can program it for other sizes, 24-volt being one of the other possible sizes. Completes a full IV curve sweep in less than a quarter of a second, so this allows you to maintain true maximum power point tracking throughout the day, regardless of shading and intermittent clouds. The controller allows for parallel operation, multiple controllers from a single source input. It has extensive networking and communication capabilities. And the last bullet here, this controller accepts power from oversized PV arrays without damaging the controller. So if you have a large 6 kilowatt array on a very, very sunny day and it's inputting power into the controller above the controller's nominal input power rating, it's not going to damage the controller, not going to void the warranty. The controller is just going to input or current limit the output to the batteries. And what we're taking a look at here are two pictures. One is the standalone of our 600-volt controller with the transfer switch, and you can see the SKU here. If you notice the little TR at the end of it, that's the way to definitely know for sure that you're talking about our 600-volt controller that has the transfer switch. So this is the one that's going to be used in the retrofit. And over here on the right, what you're seeing is our controller that is attached and pre-wired to a Morningstar ground fault protection device. And you can see the SKU ends in TR-GFPD. So we definitely recommend using our controller, and in fact, many of the code requirements, depending on your location, will require attaching a GFPD to the 600-volt controller because it's high voltage. So you can either get this pre-wired, or if you want a different configuration, you don't want the top-bottom configuration, you want it side-by-side, you can order these separately. In other words, order the GFPD separate and the controller separate, and then wire them yourself. So either way is fine. And what we're taking a look at here, we've kind of accentuated the switch on the controller, and you can see the label here. You see this controller is affixed with a manual PV disconnect transfer switch and also grid tie inverter terminals. If we take a look at the next slide, just some more specs on the switch. It's a 30 amp double pole, double throw break before make switch. So what this means is that this controller is either going to be providing power either to the grid or to batteries, but never both simultaneously. And as far as batteries, the battery system capacity and voltage depends on backup needs. Typically, batteries used in the Morningstar DC transfer switch backup solution are going to be smaller battery banks and lower weight, so it's going to save costs on batteries as well as installation costs and labor costs with the install of the batteries. And you can choose any battery manufacturer you want in our solutions as long as you're meeting the specs that comport with the backup design. And likewise, the inverter charger, you can choose your manufacturer, so you're not locked into any specific manufacturer as long as you're meeting the specs for the backup project. Inverter charger power rating and voltage depends on battery specs and backup requirements. And the AC transfer switch in your inverter charger can be built in, external, automatic, or manual. And we're going to take a look at an example a little bit later where we're going to show an example of an automatic switch within the inverter charger. And lastly, you have the critical load subpanel as a component that has to be added for the DC transfer backup solution. And this connects power to your critical loads, and this can be modified later on to add or subtract loads if conditions change. Last point I want to make here is that the proximity of the critical load subpanel will affect the cost. So if this is located close to your charge controller and close to your batteries, that's good because that's going to cut down on wiring and other installation and labor costs. And so here we have now, we're looking at a diagram or a schematic that's going to show all of these components installed in the direct DC transfer switch backup solution. So this is a grid-tied solution, or grid-tied system, I should say, that is operating with the grid on. There's no outage here. So in that case, what we've done is we've added our charge controller, our ground fault protection device, our battery bank, backup inverter charger with AC transfer switch. We've also added the critical load subpanel. And in this arrangement, what's going to happen is the PV array is going to deliver power to the controller, and this switch is actually in bypass mode or grid on mode. So what's going to happen is, and you can see here we've kind of highlighted that. So this controller is actually going to send power to your string inverter. That DC power is then going to be converted by the string inverter to AC power. That's going to be sent to your main service panel. Any excess is going to be sent to your utility for your credit or net metering to reduce your bill. And from there, AC power is also going to go to your backup inverter charger, and that will be sent to your critical load subpanel. And also you'll have AC power converted to DC and sent to your battery bank to trickle charge the battery to make sure that it remains fully charged in the event that you have a grid outage. Now we'll go to the next slide, and we're going to take a look at what happens when there is a grid outage. So on this slide, what you can see is when there's a grid outage, the battery bank is automatically and instantaneously going to send power to your backup inverter charger. And that backup inverter charger is going to convert the DC power to AC power, and it's going to send it to your critical load subpanel to run your most critical loads, which you've defined, which are going to be typically your refrigerator, your sump pump, some of your lights, your charging for your computer, your television, and cell phone charging. So the key point I want to make here is that there's going to be no time lag when the grid goes down or when you have an outage as to when this backup is going to take effect. You'll have power immediately for your critical loads. What isn't automatic or immediate is the charging of the batteries, hence the transfer switch. So what we've done here is after you have an outage, what you're going to be required to do is flip this transfer switch from the grid on controller off position to the battery controller on position, as you can see right here. Hopefully you can see my highlighter over here in the lower left. And in this instance, what's going to happen is the PV array, once that switch is turned, is going to supply power to the controller. That controller is going to take that power and regulate charging to the battery to make sure that you don't overcharge the battery or undercharge the battery. So that's kind of it in a nutshell. I know we're going to have some questions that come up about the transfer switch. Just to let you know, this is a manual transfer switch. Mm-hmm. We are considering developing an option here with an automatic transfer switch, but I can't give you any timeline on that, and I can't give you anything definitive. We don't know that that's going to happen, but it is something we are considering. We do get that question from time to time. So with that, what I'm going to do now that you've kind of taken a look at this system, is I'm going to take a look at some of the costs involved with this. And let's go ahead to the next slide. And what we've done is put together a cost comparison where we're operating the controller with full power, and we're comparing typical AC coupling backup solution and a Morningstar DC direct transfer switch solution. And you see that there's a big cost difference, and we'll kind of get into why that's happening. As you can see on the far right here, there's a pretty big cost difference for some of these line items. So I know one of the things that's probably jumping out for people, Doug, here is we're talking about the battery bank in an AC coupling solution versus the battery bank size in a Morningstar solution, and we're looking at a 600 amp hour battery here, and with the Morningstar solution, only a 300 amp hour battery is needed. So it kind of begs the question, why the 600 amp hour battery in a case where we're looking at backup for a 6 kilowatt string inverter system? So what would be the best answer to that for people?
Yeah, Mark, this is what I was talking about with the battery bank sizing based on maximum charging current. So in this case, you have the 6 kilowatts of a string inverter array, and you got a 600 amp hour or larger bank requirement for that much charging. Basically, this is what inverter charger manufacturers and battery manufacturers suggest this as a maximum charging rate. It's basically 1/5 of the amp hour rating of the battery. So with a 6 kilowatt string inverter, you can expect to see maximum charging currents of about 120 amps, and this will prevent over charging that battery too fast and possibly damaging it. And especially with AC coupling, a lot of people are sizing it smaller just to make it more cost effective. It's not really a better solution. It's just making it so it's a affordable solution or a solution that's needed by the customer to meet their needs. But in some cases, it can be undersized batteries, and with AC coupling, with the on-off switching, if it's an AC coupling without the ability to reduce power, it can limit with on-off switching, especially. That battery bank is really going to be the higher you make the current, the worse the effect of on-off switching on the max charging. It has to shut off sooner, and so you're going to be at a very low state of charge by undersizing that battery bank, and your battery bank is really crippled in that kind of situation. Whereas if you limit the charging rate, and you can do what, according to the many manufacturers, suggested maximum charging current, and get ours down to 300 amp hours. That's based on 60 amp max charging rate, and 5 times 60 is 300 amp hours.
Okay, so to sum it all up, it's a recommendation from battery manufacturers and inverter manufacturers as to this combination, 600 amp hours for a 6 kilowatt string inverter system. Terrific. Okay, so moving on, the next item is I'm looking at here, there's a difference. We're using 2 4.4 kilowatt inverter chargers with BOS here for the AC coupling solution, and only 1 4.4 kilowatt inverter charger with the DC direct transfer switch solution. So again, this begs the question, how come in this situation you're going to need 2, and ours you're only going to need 1?
Well, here again, it has to handle the full string inverter system because it's always going to be putting out max power. And there are some inverter chargers that can handle, that work with, inverters that can reduce power with higher wattages. But if you're working with an inverter existing string inverter, or if you have an inverter charger which cannot integrate with that inverter to reduce power, you're going to be having to deal with max power from the inverter system. Especially even if you have diversion and you think, oh, well, I'm just going to have diversion, it's going to solve everything. If you switch on that inverter, it's going to come on at 6 kilowatts, and that inverter charger is not going to be able to deal with it, and you could damage it, or it's just not going to, it's just going to shut off. So these are, basically AC coupling sizing limitations.
Okay, AC coupled is required to have at least or more than the 6 kilowatt string inverter system. The Morningstar is independent of the string inverter system. Okay, and we see here a huge cost difference of, because of this situation, $3,300. Okay, and then with the critical load subpanel, either system is going to require pretty much the same installation cost for a critical load subpanel. So that's pretty much going to be washed there. Next couple items, the controller with the GFPD is something that's only going to be installed in the Morningstar DC direct transfer switch solution, so you're going to incur costs of $2,300. And this is all these costs are taken from popular listed online dealer prices as of August 2015. So actual costs could vary, but these should be pretty close to what you're going to be finding if you go on the web to look at this. And then lastly, you might need a PV disconnect, possibly, so we've thrown in that as well. But when we add up all these cost differences, we're still looking at something pretty big here, over $5,400 cost difference. The Morningstar cost in this case, we'll show you what we're backing up here on the next slide. Some of the equipment cost for Morningstar is $10,650, and for AC coupling is just a little over $16,000. So it's a pretty big savings here. So if we go on to the next slide, did you want to pipe in, or do you want me to just kind of give an overview of this to let people? This is what we're actually backing up in the previous example. So it's a pretty robust backup. If you look at all of the loads that we've listed here, you're going to have your refrigerator backed up, your LED lights, your internet, your laptop, your cell phone, your TV entertainment center, your well pump if you do have a well, your gas furnace blower, and your washing machine. So this is a pretty robust backup. And what we've done is, this is the way you want to do it. You want to list all your loads that you have to back up and the quantity of each of these loads. And then you want to get the power rating of each of these loads. Lastly, you want to know the operating time, the hours per day that each of these loads are going to be operating. And once you have that, you can take the product of all of these three columns. In other words, you say quantity times power rating in watts times operating time in hours per day, and you get your energy consumption in watt hours per day for each of these items. And then if you add up all these items, you come up with a total here of 6,634 watt hours per day.
Yeah, and this would be about, with this size of a battery that we suggested, was a 14.4 kilowatt hour battery bank with a 300 amp hour 48 volt compared to a 28.8 kilowatt hour. So you've really cut the size of the system. You use an inverter charger. You may not need to go to a bigger inverter charger, and then you can still power the same loads as you might want to, or you might have to reduce, but you're making it you know, a lower price point, so you have that to offer if customers want it.
Okay, so I think what we're going to see on the next slide is,
and another point, you can always go, that number, you know, you can always go to a 400 amp hour battery or 350, whatever the battery you find can be fit into this. And on the next one, we're going to show how to fit in an even smaller battery.
Okay, let's take a look at that. And so there's a couple things here. So what we've done is we've now we're using our charge controller set at the 30 amp output.
Yes.
Rating,
so,
right?
Yeah, the controller can be set with a lower maximum output current rating, current setting. So if you set it for 30 amps, you won't put out more than 30 amps at any given time, and you can, with that 30 amps, you can size your battery bank, you know, effectively and without any worry about damage to the battery, down to 150 amp hours there. And this is the same 6 kilowatt string inverter. And remember, this is not losing anything on cloudy days. The only days you're going to lose power is on the sunny days when you have plenty of power, and at a charge rate of 30 amps, you're going to be fully charged in about 5 hours or less, and you won't need all that excess power for these loads. You know, depends on how much you want to back up. If you have a lot of loads and you just want to keep stacking them up there, you need bigger battery banks, and you know you want to maximize your charging current. So.
Okay, so in this example, we were able to use a smaller battery and also a smaller inverter charger. So we're now reducing the costs on the battery and the inverter charger here, so that the cost difference between the AC coupling solution and the DC transfer switch solution is even greater here. So we're looking at about $6,900 first line item, $3,600 the next. Again, this is a wash for the critical load subpanel. Then you have the charge controller kicking in. Bottom line here, it's kind of funny that these numbers just match up exactly, but not only is the cost happens to be $8,050, but the savings happens to be $8,050 as well, because if you subtract these two numbers here, some of the costs minus some of the costs, so you have a 50% equipment cost savings.
I wanted to say here, you know, I mean, we're not trying to say that a 33.5 kilowatt inverter charger is worth as much as an 8.8 kilowatt inverter charger. But if your loads don't require an 8.8 kilowatt inverter charger, why wouldn't someone want a smaller inverter charger if they have the choice? So that's really just a matter of, you know, we're not trying to compare our solution as, just as much as the solution we're compared to. It's just a lower price point that you can offer for people that don't want to just say, okay, I'm getting a huge battery bank, 28.8 kilowatt hours. I want to use a smaller, more reasonably sized battery bank, something that's not going to take up a lot of space and require a lot of installation time and energy. This would probably that's going to weigh a lot less.
I actually have somebody who wants to see an even lower cost solution. Can we get that going?
Yeah.
Can we do it? I have somebody just chimed in here with a question. We have a lot of questions that are building up here, but so let's take a look at this. Now, walk us through what's going on here. We set the controller to 24 volts and 30 amps now. So, and you're going to see on the next slide after this, so we're backing up less loads in this scenario. We'll show you what's backing up, but if we walk through the cost, so now we're having a 150 amp hour battery, but it's a 24 volt rather than 48 volts. So that's why the cost is even lower here. And then the inverter charger is even smaller because now we got down to a 2 kilowatt. So these costs are really, really getting small. Cost difference is starting to really get huge here. When you look at the battery bank and the inverter charger, even with the controller, you're still looking at almost $11,000 cost difference. I guess really what I should be focusing on here is the sum of the equipment cost for the DC transfer charging is just above $5,000, which is pretty darn low. So you can see a really huge difference now between an AC coupling and a direct DC transfer charging solution. Only a little over $5,000, 68% equipment cost saving. Again, we're basing this on popular listed online dealer prices, and we're not including labor costs here, but I think this is going to be really the bulk of your costs in the system. So let's just go to the next slide to, unless you want, is there something
I just want to say something more here. One thing I want to remind people is that this is the same size 6 kilowatt PV array. And this is what I'm talking about by, you don't have to reduce the size of your PV array, and you're still connected to the grid-tied inverter. So you're still getting 100% efficiency. I mean, the best efficiency you can possibly get 96% or higher, typically within maybe 96% for selling to the grid, and you don't have to give that up. But then you're connecting your full PV array, 1/8 to 1/8 is the charging. So basically, you're going to have 30 amps of charging even on cloudy days. There will be probably the worst day of the month, you're going to be at like 50 or 60% of that rating. You'll probably still be getting some charging. But that's the kind of thing where it makes the charging real consistent. People might say, well, it's going to cost me less just to put in a small little 24 volt DC coupled solution, but you're not going to get you're going to get variation on the charging, and you can't do this kind of charging with 30 amps even on a very cloudy day. So
okay, well thanks. Let's go to the next slide so that we can see what's being backed up here. So we can see we have less loads being backed up, and that's what allows us to provide this smaller solution or less expensive solution. What we are backing up, though, is still the refrigerator, freezer, some of your LED lights, your internet, your laptop, cell phone charger, and your television. So not too bad. Some people, this might fit their needs. And again, it's just over, as far as equipment costs, just over $5,000. So yeah, I'm glad we were able to put this together. Is there anything else you want to? Yeah.
So the battery bank, 24 volts, 150 amp hour is about a 3,600 watt hour battery bank. And one of the things I want to say, it's better to reduce the current on a 48 volt before you, and then only go to 24 volt with lower voltage inputs, because it will derate above about 400 volts or so, but it will continue to operate at 50%, no problem, up to the maximum VOC of 525 volts.
Okay, terrific. So I think at this point, what we're going to do is take a look at some of the questions that have come in. So again, if you have questions, just go ahead and chat them in the chat box at the bottom. I know we had a question here that came in about whether we can use this Morningstar DC transfer solution with Enphase. So you want to go ahead and take that,
sure,
that question?
Sure. Yeah, this is not compatible with microinverters. Of course, it's a 600-volt controller, hence it's a 600-volt DC system. So these are string inverter systems that we're looking to back up. String inverters are pretty common, and especially older ones, and so that would be mostly for string inverters. There are certain optimizers that are not compatible with all inverters. We can set our controller for constant DC voltage, but still not compatible with certain types of inverter manufacturers that have specially made optimizers that are limited to operate with that manufacturer's inverter. We have talked to these manufacturers and are willing to get it to operate at a fixed input voltage, but so far that is not currently an option for certain optimizers. As far as I know, some optimizers work well with our controllers.
Okay, I think I'm looking at some other questions here. This looks like a good one that came in from Brian. What is the adjustment range for the controller's max amp output? Could it be programmed for as little as 30 amps of output, for instance?
Exactly. Yes. That's exactly what I was talking about with our example. So you can dial it down. If you had a 400 amp hour battery, you can even dial it down to. If you had 400 amp hour with 48 volt, or actually a 200 amp hour battery, you can dial it down to whatever maximum current you want. So you can create a fixed output current.
Okay, terrific.
We have maximum output, I should say.
We have a question coming in from Rick that says, can the system be mounted outside of the building in the weather?
It would have to be inside of an enclosure. So this would be an option which could be good, since it might not require something like remote shutdown requirements for 2014 code. But if it's a ground mount and it's outside, you can do that. Or if it's on the side of a building, you'd have to have it so it wouldn't get wet. So basically, it'd be inside of an enclosure or under some kind of cover, or some kind of awning or something to prevent any rain from reaching it. So it's indoor rated.
Okay. And a couple other questions came in that ask, is this compatible with Solar Edge?
Oh, Solar Edge. Oh, that's one of the optimizers that I was talking about. That I think those optimizers are only compatible with Solar Edge inverters. So no, it would not be, just as any other inverter, would not be compatible with other inverters, as far as I know. There may be optimizers out there that it does work with. Any optimizer that works with most inverters should be possible to use it with ours. One of the considerations is that if it reduces max VOC, it may not be optimized. Those types of optimizers may operate at too high of a voltage than you would want. So you want to still size it the same, whether the optimizer can limit voltage or not in some cases.
Okay. Well, we're kind of running up against the clock here, but let me see if we can take one more. It's getting tough because a bunch of questions are filing in, and as soon as I try to read one, the screen moves. So let's see. Somebody did ask a really good question that kind of moved. Well, we got a couple questions about warranty. So what's the warranty on the controller? You want to?
Yeah, these controllers have a 5-year warranty. We have discussed extending that somehow. Maybe that's something we're going to offer a automatic switch possibly at some point. We might also consider offering an extended warranty, but we don't have any of that plan in place at this time.
Okay, here's a good question from Matt that came in. Yeah, I think this is the last question, but does the inverter charger supply power back to the grid during normal operating mode?
Oh, that's a good question. So yeah, you can use this switch anytime you want. So if you wanted to, you can, as you know, the inverter charger will maintain the battery voltage and float voltage when during grid operation. So the inverter charger, just like an AC coupled system, will maintain battery voltage, and then you can use a switch even during grid-tied operation. If you have it sized like with a single string or something, you can switch it over to get high efficiency battery charging, especially if you're talking about, you know, midday power reduction. It's a manual switch at this time. This would be one place where especially the automatic switch would come in handy to make that go into charge mode whenever you want, and then you get really high efficiency and make it very cost effective for those type of situations, or at least the charging is more efficient. It may, whether it's cost effective, you're adding backup, it would have that ability to sell to the grid.
Okay, well, thanks everyone for joining. We're going to wrap things up. Thank you very much, Doug, and we'll see everyone next time. And if you do have any questions, just feel free to contact us at morningstarcorp.com in the Contact Us section. And if there's anything that we didn't cover that you need to go over, please send those questions. And until then, we'll see you next time. Thanks so much.